is adaptive meshing, which is something that I've kind of recently gotten involved with because one of my colleagues has at KU is really interested and spent a lot of his career developing what he calls moving mesh methods. Okay, so these are for time-dependent PDE problems. And then I also have gotten into, and this was actually started as a student-oriented project on reduced order modeling techniques, and we've tried to eke a little bit more out of particle filters using some of these. So these are the topics I'll try to hit today. Let's see. Got it. Okay. So. Do it the old-fashioned way. So in 1904, Wilhelm Birknes proposed this idea of basically combining models and data to predict weather. Okay, and a few years later, Lewis Fry Richardson tried to do this. Okay, so solving some of the basic thermodynamic equations and essentially forcing them with data. Okay, and so the PDEs were solved, and I call it numerically by hand because they were discretized and then they were solved by hand. Okay, this is before the advent of computers, and the grid spacing was pretty big. Okay, in comparison, I think the grid spacing used by ECMWF these days is 9 kilometers for kind of a large scale weather model. So this is only really an order of magnitude larger grid spacing. The results that Richardson got were not good. They were way off. Okay, imperfect model, coarse discretization. The observational was sparse and non-smooth. Okay, so things were out of balance, and so kind of as a a post-mortem, so to speak, Lynch went back and tried to see if we could take what Richardson had tried to do and use some of the modern ideas that we use now and see if this experiment could be done successfully. And actually with a little work, there's CFL conditions, making sure those are satisfied, smoothing data. It worked pretty well. Yeah.
You can go full screen by pressing Command and L.
I know, it just wasn't showing up.
Okay.
It's the. Let me see if this one. So this is a schematic I like. This is, I don't know if you can see it, but there are people here. And up here is kind of a controller, and the controller is telling certain people to go faster or slower so we can synchronize so I kind of like this. This is like a human supercomputer. Okay, the compute nodes are all people. So this is kind of an envisioning of a forecast factory. Okay, so now it shows up on my screen that I've changed the.
I think you can switch the screen you want to share. Press share screen. You can choose between two screens that you want to.
Okay. Well. Okay. So what's behind Bayesian data assimilation is Bayes' theorem. Okay, so Bayes' theorem, what we want is we're trying to find an initial condition for a set of differential equations conditioned on some data that we get. Okay, and the way we do that is by calculating a likelihood and a prior. So Bayes in words is that the posterior is proportional to the prior times the likelihood. So if the observational noise is Gaussian, for example, normal with with mean zero covariance R, then we can write the likelihood, right, as an exponential, right, like this, where the argument of the exponential is this J, okay? And if the prior is Gaussian, then it can too be written in a similar way, right? And so if we multiply these together, then we have what's basically going to give us something equivalent to what people call a simple Kalman filter or a 3D variational approach. Okay, and so if we want, right, we can just do the calculus, right? We can go and say, oh, I have this cost function that I want to optimize, right? And in this situation, if H is just a matrix and this is a quadratic cost function, right? So we take the gradient, right, with respect to X, and we have a linear system of equations that we solve. And so that solution, the solution that we get, this XKA, is the same thing as what we get through the use of a Kalman filter. Okay, so this is optimal interpolation or Kalman filter, 4D bar or 3D bar, there's this equivalence between them. Now, if we want to put more time, right, K now is going to be time, right? We have to deal with the fact that our model, our solution operator for our PD model is not likely to be linear. So we've introduced a lot of nonlinearity here. Okay. So here's kind of the setup that I've employed, and I'll employ in this talk. And here n is time. Okay, so I have, this is my solution operator. This is some omega is some additive noise. Un are the state variables. Okay, I'm going to assume that the additive noise is drawn from a normal distribution. And we also, together with that, have some observational data. Okay, so the H is the observation operator. This UN, T is the truth at time n. It has potentially some additive noise as well. And H takes us from our model space of our state variables to the space of the observations. And the space of observations usually lower dimension. Okay. And H doesn't have to be linear. In a lot of what I'll talk about, I'll just take H to be a linear operator. Okay, and I want to just go through some of the common techniques that are used in data assimilation. One is the ensemble Kalman filter, right? We make a forecast, right, with L ensemble members. We can find a forecast mean and a forecast covariance, okay? And then what we'd like to do is we'd like to take the data that we have and nudge things so that we feel the influence of the data, okay? So in the analysis step, we calculate the Kalman gain, right? And then we update the forecast by the Kalman gain times what's called the innovation. So if the innovation, if this yn y minus hu, if this is 0, right, or in the null space of the Kalman gain, then the analysis update is the same as the forecast. Okay, so there's many variants to this. One is the transform or square root filters that employ perturbations that are consistent with having a Gaussian posterior. Localization is very important for the success of these methods. That means we have to kind of restrict the influence of the observations. You know, we don't necessarily think, especially if it's, well, I guess it could be snowing here too, but If it's snowing in New York, that weather data we get in LA is going to be good for predicting things in New York. Variational methods we kind of saw on some of the earlier slides, but they take a cost function, right? And here, this UN, and I've kind of hidden the nonlinearity in here because this UN is going to evolve based on our nonlinear differential equations. Okay, so this is still a function of U naught. So this is flexible. We can put other terms. It's nice. These variational techniques are nice because we can add other terms. It's fully nonlinear as long as we, iterate this, do a kind of a Gauss-Newton method, and it's kind of, we can do this over intervals of time. Okay. The common filter is sequential. We take the new data and then we update, and then we go to the next time of observational data, and then we update again. One thing, and this is something that's led to a lot of recent research, is that we don't have this uncertainty information we get with the covariance matrices. Here we really get the mode, whereas with a common filter type technique, we get a mean and a covariance. Okay. So there's hybrid techniques trying to get the best of both worlds, trying to get some of the nice properties of the common filter together with the ability to deal with the nonlinear terms that we get from the variational techniques. So there's a number of these types of, and this is, I think, still a very active area of research. Particle filters. This is something that Maddie's made some real fundamental contributions to. Basically, don't use they use a more unstructured representation for the posterior distribution. So instead of a mean and a covariance, it's like we have these point particles and we assign them weights. Okay, so here this is the weights are updated by so I here is this is the I particle or ensemble, right? So the old weights, the prior times the likelihood is the posterior again. Okay. C is just some number chosen so that the weights sum to 1. A lot of interesting in variance and implicit particle filters, equivalent weights, optimal proposal that I'll talk a little bit about, particle flow filters, trying to get localization into particle filters is an ongoing endeavor. So I want to look for a moment at the computational complexity. So I'm going to let M denote the dimension of the model space where our differential equation lives, the state space differential equation. D, the dimension of the data or observation, and L, the number of ensembles. So an efficient ENKF has a computational complexity that looks like this. Okay, so I mean, we'd love to have large ensembles. We're going to approximate things better. We have the large numbers is going to kick in. But in many practical applications, we really can't afford to make L too big. M is this model dimension, and then so this is kind of, we'd like to reduce this. We'd like to make these methods, we'd like to make them more efficient. For particle filters, the cost is essentially this. And one of the difficulties with particle filters, and this is true of I think most, if not all, particle filters, is that the theory says to avoid what's called filter degeneracy or weight collapse, the theory requires that we have an impractical number of particles or ensemble members. Right, so this is not practical. So we have this curse of dimensionality. I use this as another motivation to try to employ dimension reduction techniques for particle filters. So in high dimensional geophysics applications, you know, like in numerical weather forecasting, we'd like L around 20. Okay, so we have very large models, and I guess this is getting cut off, but the general rule of thumb is L. We want to cover the instability, the kind of, so one of the things I've worked on in my career are these things called Lyapunov exponents. And Lyapunov exponents are kind of like real parts of eigenvalues, right? But they're from for a more time-dependent situation. They kind of generalize the real parts of eigenvalues. There's what I would call a stability spectra. They tell us about linearized stability. Okay, so the number of positive Lyapunov exponents plus the number of kind of neutral or close to zero Lyapunov exponents. Okay, so that makes things hard when we have a lot of turbulent flows and things like that, where we have where we have a large dimensional attractor, large number of positive Lyapunov exponents. So the things in blue are kind of where I'm going to live in this talk. The reduced order modeling. This seems to have a lot of nice acronyms: dynamic mode decomposition, proper orthogonal decomposition, principal component analysis. There's a nonlinear theory that's being developed called Koopman theory. You know, the use of adaptivity is something that I think has been very successful in the solution of differential equations, but it's something where I think there's a lot of nice possibilities when it's combined with data assimilation. So there's some works, mostly for one space dimension PDE, for adaptive spatial meshing for data assimilation. I'll describe some techniques we've developed that really work in you know, for 2 and 3 space dimension PDEs that we'd like. And then these reduced order modeling techniques for particle filters were motivated by work that goes under the name of assimilation in the unstable subspace. So this is based on this kind of dynamical systems, Lyapunov exponent-based theory. Okay. So why do we want to use adaptivity? Well, I mean, adaptive techniques in space and time, you know, we're trying to be more accurate, right? We're trying to focus grid points where more resolution is needed, like near shocks or sharp fronts, right? Hopefully more efficient by using fewer grid points. Okay. Adaptive in time stepping techniques, we do adaptation all the time. We set a tolerance. If you go into MATLAB, this is, you know, you set an absolute relative error tolerance, and it chooses the time step so that the estimate of the local error satisfies these local and relative error tolerances. This is now doing adaptivity in the spatial domain. Okay, so for ensemble-based DA, and that's really kind of my focus in this. There's a lot of opportunities, I think, and definitely some challenges. A lot of computational models allow for an adaptive discretization. Okay, a lot of the DOE climate models, and I know the NRL climate models, the Neptune and COAMP, they allow for for a non-uniform grid. Okay, so we want to have accurate ensemble members, and we don't want to introduce a lot of error in the observations. Okay, so we want grid points close to where we're observing data. There's a desire, and this is the kind of the trade-off, to minimize interpolation and extrapolation. So if I'm constantly updating my mesh, I have to somehow evolve the solution onto the new mesh, or interpolate from the old mesh into the new mesh. That takes time, right? And that introduces error. So we're looking into ways to minimize that. And we want to optimize different aspects of the DA through the choice of mesh. So this is where, because the end goal is different in DA than in just solving numerical PDEs, we want to bring some of these factors into play. So there's a natural competition between the representation error ensemble and representation error in observations. Okay, so this is the first thing we try to do, is try to balance these things a little bit. And the time evolving are used to both obtain accurate, efficient, I think I've already said this, without using a fine mesh throughout the domain, and to track and kind of accurately represent features, coherent structures, eddies, gyres, things like this in our model solutions. Okay, so here's a kind of a simple example. I spent a lot of time looking at these two equations. Yeah.
Quick question from the previous slide. Are the locations of your sensors in space time dependent, or are they fixed?
Could be either.
Could be either.
Could be either. Yeah. Yeah. I think the results I'm going to show today, they're fixed, but we could potentially deal with like Argo floats or something like that, where you got to figure out where they were or where they are. Okay, so this is just a simple example. So of what I would call the moving mesh PDE method would be. So if I take this term out, right? What this equation right here is this is a discretized one space dimension PDE. Okay, and this is a non-uniform discretization of a second derivative. Okay, and this is just going to be a nonlinear term. Okay, and so what we're going to do is, since our mesh is going to be moving in time, we get this extra term, this advective term right here. We take the total derivative with respect to t, right? We have u of x and t, but now x depends on t. So that gets us this term right here after this has been discretized. This is like a ux term, right? This is like ux x prime. Okay, and then this scheme, the monitor function, or the measure, kind of the measure of difficulty we're going to use is arc length. And what we're trying to do with these equations is to choose a mesh so that as I go through the solution, the arc length is uniform. Okay, so I'm going to adjust my mesh points so that the arc length between any two grid points is equal for independent of which two grid points. Okay, so effectively, this is a way to say, okay, here's my discretized PDE problem. Here's my here's my equation for the mesh movement, right? Depends on you, so it's kind of a coupled U and X equation. And where we're moving is to just replace U with a monitor function. Okay, this gives us this flexibility that allows us to kind of expand this to other situations, not just, okay, here's this reaction. If you bring in other things that may influence the skill of the DA. And so in practice, what's done is these are not solved as coupled equations, but one is solved, right? I fix the mesh, solve the PD, then I fix the PD and kind of in a pseudo time, if you will, update the mesh. Okay. So there's some existing techniques that I'm going to go through really fast. One, this common mesh idea is trying to make it so this is like doing data assimilation with ODs, right? With ODs, I know where I'm going to try to update things, right? And now I've got all these ensemble members. I've got the observations that, you know, they can be in totally different places than where I have concentration of mesh point for the PDE. But I want some central place where we can update and bring in the data and yeah, do the analysis. Okay, so there's these common mesh approaches. And so what we did is we took this metric tensor based approach, right? Metric tensor monitor function. And a metric tensor is just, it's locally just if I'm in one space dimension, it's just a positive scalar, right? And if I'm in, it gives me some information, some about anisotropy, but it also gives me some information about size. So the way to think of a monitor function is it's kind of inversely proportional to the mesh spacing. Where the monitor function is large, the grid will be fine. Where the monitor function is small, the grid will be coarse. Okay. And there's software out there where you say, oh, okay, I want a mesh. I want a mesh. So I give it a monitor function or a metric tensor, and it will return an approximate M uniform mesh. A mesh that with respect to this metric tensor is uniform. Okay, and so we want to combine metric tensors to determine common meshes. And let's see, it's cut off for me too, I think. So, okay, so this metric tensor intersection, I'm going to skip over this. So here's a way we constructed a kind of a mesh that was kind of good, but for a whole bunch of ensemble members. We take, okay, we have these metric tensors that correspond to the mesh that of the individual ensemble members and take this intersection, okay? And the best way to, I think, is with a picture in this case. So I have this is in 2 space dimensions, okay? And I have this 2 by 2 positive definite symmetric matrix describes an ellipse, right? So I have 2 of these ellipses, and when I take the metric tensor intersection, what we get is the largest inscribed ellipse. Okay, so this is a way for us to combine, okay, this ensemble member wants things fine here, this one wants things fine here. How do we kind of make an average metric tensor, and that will then correspond to an M uniform mesh. All right, so for the mesh points near observations, we kind of just came up with an ad hoc metric tensor, right? We use an indicator function, so the XJO, these are these are potentially time dependent, and these are where our observations are located. And this was just some choice that seemed to work well. That's exponential. This was a scaling factor here, so that the metric tensor for the ensembles and the metric tensor for the observations, were of the right scale. And then we can define the combined one that takes the metric tensor for the ensembles together with the one for the observation locations, and we can potentially use that as the place where we do the analysis update. And so here, I think this will show up. So the red stars here are the location of the observations. Okay, this is a 2D inviscid Berger problem. Okay, so hyperbolic PDE, that's been a challenge too, is getting these moving mesh methods to work with hyperbolic problems. Okay, and this was just started with a Gaussian bump, and it just kind of transports and vects along this 45-degree line right here. Okay, and so here, this is just, if I just took the ensemble mesh, we got something that looked like this. But when we combined with having mesh points that are clustered near the observations as well, we see this here. So this has kind of got both things. It's got the ability to resolve well the ensemble solutions, but also the ability to avoid big interpolation error for the observations. Okay, and so this is just a simple schematic of what we're doing. We combine and get a common mesh, interpolate, update, and continue. So we've done work on inviscid Bergers in 1 and 2 space dimension, a shallow water problem in 2D. So these are hyperbolic PDEs. So we've adapted a discontinuous Galerkin finite element method with explicit, and this is kind of a problem, but implicit is hard in this case. We're working on it, and a DG based interpolant. Okay. We use my colleagues' freely available MMPDE lab. We get the metric tensor by using a recovered Hessian. Okay, so this is kind of a similar to that arc length monitor function. We use this Gaussian indicator to get the observation mesh. We use this local ensemble transform common filter. We use this metric tensor to define some localization and compare this to a fairly commonly used one called Gaspari-Cohen. And we again use the metric tensors to combine things. This is a lot of detail that I'm going to skip over. This is basically where we get that meshing functional. We're trying to keep the error distributed equally between the different elements in our computational domain. And there's also an alignment condition so that we don't get small angles, right? We want a well-conditioned problem. And we use this to define a meshing functional. Okay. The nice thing is this works really well. I mean, I'm not with this approach, and it doesn't preclude it. I'm not adding or subtracting mesh points. I mean, that can be done. That's a rezoning step. But we've had really good luck with the problems we've looked at where we don't get the meshes becoming singular. We don't get small angles. We don't get mesh points colliding or overlapping. So it's very robust. Okay, so here's an experimental setup. We're just using diagonal covariance matrices, 10 trials, time between observations. With some of the localization schemes, we did some tuning. So when we do the comparisons, we're comparing tuned techniques to tuned techniques. Okay, and our goal is to get the RMSE to be the order of the square root of beta, where this is the observation error covariance. Okay. And so this is the localization scheme using the metric tensor. So here, this is an isotropic version, right? We just use the determinant of that metric tensor at the ith mesh point. And we're going to compare this to using a polynomial cutoff. Gaspari-Cohen, it's a fifth order compactly supported polynomial. And so this is the kind of Invisit-Berger equation we're using, periodic boundary conditions, we're solving on a square, we use a Gaussian bump initial condition, and we perform at least as well as this kind of standard, and learn some things about localization since I'm here. So it'll be real interesting to go back and look at this again. And another thing we experimented with is on this slide, the top figure is we use this kind of structured interpolant when we interpolate between meshes, and the bottom one we just use a very standard linear interpolant. And so we see some advantage, right? We're below, this was our target, 0.1 for this experiment. And we do better. So here, this is the combined one. This is just using the observation-based mesh, and this is using just the ensemble-based mesh. And in the loc, this is looking at this is using the largest determinant of the top 10% of so this is just measuring things where the solution is steep. Let me say it like that. Loc means we look at this, we calculate the error just in the vicinity of where the front is steep. Okay, because we were worried that, since it's RMSE, that we're going to average things out, but instead we get really very nice results even in these places where the solution is.
Is this the interpolation between the solution and the observations, or between the innovation and the?
This is so when
the DG interpolate uses linear, I don't really understand why they should get use a linear DG scheme.
So
I guess I understand.
it's so for example, if you take shallow water, right, and you use the DG interpolant, you'll preserve the kind of lake at rest solution. And if you use the linear interpolant, I don't believe you will. And so it's not a huge effect, obviously, but it especially when we're using the ensemble-based mesh, it performs quite a bit. It is more expensive. So, all right. So where we're heading, we're trying to develop and combine metric tensors from several factors that can influence or impact the DA performance. So for example, sensitivities, adjoint sensitivities, for example, Lagrangian flow fields, topography or orography, approximations due to the use of data, enforcing or boundary conditions. That's one thing we're currently working on. I'm trying to kind of minimize the amount of interpolation we do by developing, especially in an ensemble situation, robust meshes that are good for a range of similar behaviors, right, over a whole set of ensemble solutions or a large interval of time. And we do this to avoid a loss in accuracy and efficiency when we update or interpolate to new meshes. And as I mentioned, we spend a lot of time trying to kind of optimize our delta T by working on the meshes to, this is within the code, but basically, CFL conditions are tough for these methods to deal with, especially these explicit methods. So we're working to develop some implicit methods. All right, so let me see. I'm gonna be. I have 7 minutes, right?
You want questions?
Okay. So I'll just try to. So what this is the reduced order modeling part. So this is basically just I call this project and truncate, right? So we're trying to generate projections with these V's, right? And we take our model and we use these projections to define a reduced order PDE model. Okay. And at the same time, we're trying to keep track of what this does to our error covariance matrices. And we're doing the same thing with the data models. We start with our original model. We started out using state space-based projections. So we use the pseudo inverse of full rank observation operators to go from, it seems a little crazy maybe, but to go from the lower dimensional observation space back to the higher dimensional state space. Okay. And then we can come up with projected data models. Okay, so given that I've used up my 2 minutes, let's see. Okay, so basically what we're trying to do is, this is something Maddie knows well, the optimal proposal. We're trying to use these. And so I think we do a weight update. We have a resampling technique that focuses. This is the generator of the data projection. So we're trying not to perturb back into the whole space. So resampling means when the effective sample size gets too small, right? We pick out some of the high weight particles, and then we perturb those and continue. So it's a very discontinuous step that we'd like to avoid. We'd like to avoid resampling. Okay. And so we use this AUS, which is based on Lyapunov exponents, PCA and POD, DMD, which is a different ansatz. We use the Lorentz 96, which interestingly I found out can be kind of considered as a discretization of this nonlinear PDE, okay, which is kind of nice. Shallow water model, U and V are velocities, H is the height. This is just a simple finite difference scheme with lax Windroff. Again, so we have a hard time with these particle filters beating these ENKF or ETKF. So this is one without localization. And the way we were able to do a little bit better was to introduce a structural error in the model. So we calculate the truth with f equal 8. Okay, this is a fairly chaotic region, but the forecasts are made with f equals 6. So this is a way to promote kind of the bimodal or multimodal, which is where we want particle filters to shine. You can see let's see if I can. So anyway, what? So okay, so we did this with shallow water. We reduced from about 38,000 variables down to about 50 variables. We can use, one thing we found is we can use these results here. I'm sorry, this isn't showing up. These results here, the DQ is 1. That's we use a one-dimensional data projection. Okay, so that's something I'm kind of excited about. This is some more recent work. I've heard this mentioned. We're trying to pick the data projection using lasso. Okay, so we want something that matches well our data, but we don't want it to be high dimensional. Okay, this is where we're kind of given these modes. We want to pick modes that are good for representing our data. And here are kind of the best results we got. We get the RMSE. This is kind of switching from f equal 8, which is a hard region, to f equal 3, which is kind of the more laminar region of Lorentz 96. And we want low resampling rates. So these green lines, they kind of give us that. Okay. And so this is back to some of my previous work on Lyapunov exponents. I studied when are Lyapunov exponents stable with respect to perturbations. That's something I don't think has been adequately looked at in this reduced order modeling community. So trying to come up with ways to have these POD and DMD modes have kind of stable stability spectra. Imposing simple rank 1 data projections and varying the rank of projections by monitoring the representation error. I mean, if we have kind of a whole range of data projections, we have a way to estimate error. Okay, and development of this is really focused on particle filters, but I'm very interested to see if these things can be helpful for ensemble common filter and 4D bar techniques. And this is some of our recent publications. So thank you.
Okay, thank you very much, Eric. That was fantastic. And if anybody has questions, we can take those now. And if anyone in the Zoom audience has questions, to raise your hand, or to put your questions in the chat, and I can read them out for you if that's more convenient. Anybody in the room have some questions?
The metric tensor.
Yeah.
It refines, or it indicates where you should refine the mesh based on the location of your observations.
Yes.
So what if you have observations that are very, very close together, but the solution of the PE you're solving is almost constant? Don't you kind of put a lot of work, grid points where you don't?
Yeah. Yeah.
Does that happen, or is there something in the?
No, it's strange because where the solution is flat, we won't make much error.
Right.
Right. And where the solution is steep, we already have a concentration of mesh points.
Right.
So it's somehow in between those two. Where I think the utility comes in. The two extremes,
No good in either.
we don't need to do anything. We really don't need to do anything. And you know, we started working on this and we're like, okay, where do we find this? And so that's why this example with the two quarter circles, you know, it's kind of not where it's most steep, but it's close enough to where that thing is advecting through that it pays off. The metric tensor intersection is really cheap, highly parallel. So combining meshes costs us nothing. And really it's you know, somehow what we'd like to do is and I think this is where we're heading is really trying to avoid moving between meshes. You know, having meshes that are everybody's gonna be supportive on these meshes for as long as we can really stand it.
Are there any other questions? Questions from the Zoom audience?
Thank you for your patience. I really appreciate, you know, it's hard to get this going and I you know, it's always fun for me to talk to kind of a non-math audience, but I often don't know where to pitch things either. So I hope at least some of the concepts and ideas came through. Good. Thank you.
Thank you all very much. I will say. Eric, there. Thank you very much to the Zoom audience.